Hi, rate determining step. I have an easy answer for you. The rate determining step is always the slow step, okay? Always the slow step. And you will have to be told what elementary steps are fast, which one is slow. There will always be one that is the slowest. So in all the elementary steps that you're given, only one will be written as slow. So when you are given a list, I have two examples here of elementary steps, and it asks for the rate determining step, bam. All you have to do is go to the one that's slow. Automatically, you would label that one as the rate determining step. Now that's going to be really significant when you want to find the actual rate equation, because when you use the rate equation, determine the rate equation, you always use the slow step. Now, two things from this. Number one, the slow step, think about this. You can't go any faster than the slowest aspect of any process. Think about walking with friends. If everybody wants to stay together walking, you always match the speed of the slowest person. Years ago, we took our 5 daughters to Disneyland, and our youngest was only 5 years old. Her legs were like, this long. I was a little paranoid, so I constantly was holding hands for 2 kids. Our oldest daughter was in the middle, and then in front of me was my husband holding the other kids' 2 hands. Well, all through Disneyland, we matched the rate determining step. The slowest person in the group was our youngest daughter with these little legs. So all through Disneyland, we were walking like this because we were matching the rate determining step. You can't go any faster than the slowest aspect of what is in that process. It's a metaphor for life, isn't it? You can't go any faster than the slowest part that's occurring in your life. Interesting. So remember that rate determining step. This slow step is going to determine the overall rate of this entire reaction. Now, second thing that I want to point out from this, you can add the elementary steps together and that will give you the true overall chemical reaction. So let's do that. You'll recall that if you have any species that are identical on both the reactant and product side, they can cancel out, just like we do in algebra. So I look at this and I want to see, are there any species that are identical? Like, oh, sure enough, I see it. Right here, that NO3 and that NO3, those are identical, so they will cancel out. Oh, notice I have 1 NO2 here and 2 NO2, so I can cancel out one of those. Okay, everything else we're going to save because it won't cancel out. Now I just add up everything on the reactant side, so I'll have NO2 plus CO yields, my only product is CO2. This is the true chemical reaction, okay? So there's your chemical reaction. That's what we would observe, okay? That's physically what we would observe. We would see there'd be 1 mole of NO2 reacting with 1 mole of CO to produce, oh, I'm so sorry. I can't go against the conservation of mass, sorry. I missed my plus NO, there we go. Plus the CO, and it will produce 1 mole of CO2 on 1 mole of NO. So there's my chemical reaction, okay? This is the true what happens in life reaction. These up here, remember, those are elementary steps. Those are reaction mechanisms, and we call that molecularity. This would be my bimolecular, and this is also bimolecular. They each have 2 reactants. So this is the theory world. Some chemist thought this up in their brain. There's no evidence for it. There's no evidence. It's where we have our activation energy diagram right up here, transition state. It's how reactants break bonds, how products form bonds. We don't know. So this is all in the imagination of the chemist that wrote it down. So this right here is going to be your reaction mechanism. It's the molecularity. Let me write that down. So the molecularity. So it was actually the chemist that came up with the idea of, hey, that's the slow step. So this is what really happens in the world, and this is our best guess of how it happens. The process of how reactants break and how those bonds form. Second example. Okay, so notice now I have the fast step first, and then it's preceded by the slow step. Now when that happens, the fast step will be in equilibrium. It will reverse on itself. And I put this note right here. If the slow step is preceded by the fast step, so the fast step is before the slow step, then the fast step is reversible. Let's look at this. Why? So this reaction is going to go really fast, okay? It's pumping out the N2O2 really quick, all right? And then it comes down here, and the N2O2 slowly reacts with the O2, okay? Slow coach right here. So this starts to pile up. You get a big pile of N2O2, and then it's a bottleneck, and it waits, and it reacts, and it waits, and it reacts. So rather than just getting this great big pile of NO2, it reverses. So you have the NO produce N2O2, and then that decomposes back to NO while it's waiting for, one of these to slowly react. Remember, in equilibrium, when you're at equilibrium, what's equal? The rates. The forward and the reverse rate are equal. So the rate at which this goes to products is the same rate at which this goes to reactants. That will also be hugely significant when we finally determine the rate law for the equation. Now, just for posterity, for good measure, let's go ahead and add these two molecular, okay, this is the reaction mechanisms that some chemists dreamed up in their brain, theory world. Let's add these together to get the overall true reaction, okay, what really happens in nature. So I'm looking for anything to cancel. Here we have it. We have the N2O2. Those are going to cancel. I think that's it. So I have 2 of the NO. I could write it like this. 2 moles NO. And I could have written 2 NO up here as well. Plus O2 yields 2 NO2. Now, quick question for you. Again, which one's the rate determining step? The slow step. You just write down, bam. This is going to be the rate determining step. How those two reactants, the speed at which those react, is going to determine the overall rate for that reaction. Okay, now, if you have any questions on this, this is just moving us to finally writing the rate law for overall reactions. If you have confusion on this, go back and watch my videos on terms for reaction mechanisms. Also look at writing rate equations for intermediate steps. And watch how to watch the orders from elementary steps. Okay, thank you. Have a good day.